Hello and welcome back. This is Matthew, and today I want to show you a pretty great workflow to do C development in Linux targeting your MVS 3.8 mainframe. So I'm going to show you the finished product first so you know what it is that I'll be showing you how to set up in this video, because it's really cool, and I think once you see it, you're going to want to do this as well. So I'm in TSO here, right? This is my MVS 3.8 system. And I'm going to try calling a program that doesn't exist yet. So I have a PDS called load, which will eventually have an executable called hello in it. So if I run that right now, it says member hello not in dataset in wilson.load. And it's asking me for a different member name that does exist. Well, nothing's there. So let me send a PA1 key to interrupt TSO there, and we're back at the ready prompt. And I do that just to show there's no funny business. This program really doesn't exist already. So now let me switch over to my Linux shell. And I have a hello.c file here. So simple stuff, it should just print hello TSO. But of course, this could be whatever C program you want. Now I'm going to type make install, and you can see a bunch of stuff happened and the make file finished, and I'm back at my shell prompt here in Linux. Now if I go back over to TSO, if I say call load hello, it says hello TSO. So we're writing our C code over on Linux with whatever editors like Vim we're comfortable with. We can say printf, that was neat. How does make install in Linux send, I'm going to run out of room here. Send a load module to MVS. And we'll just make install again. Switch back over to TSO, call load hello. And of course we have our updated program. So that very question, how does make install in Linux send a load module to MVS, is what I'm going to answer in this video. So stick around. I'm going to reset my system here back to how it was before I did this setup so that we can walk through doing this yourself. I'll be back in a minute. For you, it will just be a second. Okay, welcome back. So let's dive into how this works. First, I just want to say this entire idea comes from when I was looking at some work that Tommy Sprinkle had done with some of his C code for MVS. And I downloaded some of the source code for that. I noticed a make file in it. And I started looking at what the make file was doing. And I thought, oh, yeah, of course. That's really clever. And that should work. And sure enough, what his make files do is what I just showed you over in Linux and TSO, right? From the non-MVS system, we're able to write C code and then just have a make install command that magically, although we'll see that, of course, it's not magic, it's just a smart way of doing things, gets your executable code over into your MVS system. So Tommy's code, it looks like he's working on Windows and uses the Cygwin environment. I, of course, work just directly in Linux, and we'll be making some slight adaptations to make everything work from Linux. But this idea, I don't know if this was Tommy's original idea or if this is just a known technique in the community of users who are writing C code with Jcc for MVS. But regardless, everything I'm about to show you is just an adaptation pretty directly of what I learned from the make file in Tommy's projects. So all thanks and credit certainly goes to Tommy Sprinkle for inadvertently exposing me to this idea. So let's get going. The C compiler we're going to use is the Jcc Compiler, and then also its C standard library for MVS. Now this was developed by Jason Paul Winter. Unfortunately, the website where it was distributed has been offline for a long time, 4-5 years now, or longer. But luckily, the Internet Archive has a complete copy of the site and the download package. And it's also included in TK4-. So it's all set up to actually use within MVS. So I should say JCC, it's a C compiler that comes with executables for Windows, Linux, and MVS. So you can compile your MVS code from a host system of Windows or Linux, and it acts as a cross compiler in that case. Or you can compile directly on MVS, and then it's just a C compiler that's available to us for MVS. So that latter scenario is set up in TK4, and the original zip file is also just stored in TK4, so you can grab it from there, or you can grab it from the Internet Archive. And we're also going to use another utility called Reader Prep, originally written by Jim Morrison, which he posted to the Yahoo Hercules group. But since that's no longer available, Jay Mosley, a name we see often, makes Reader Prep available for download and talks a little bit about it as a way to get data to your MVS system in his MVS Frequently Asked Questions. So let's download these so we can get going. I'm going to copy the link to the JCC download package. Copy that link. Switch back over to my Linux system here. So I just made an empty directory called C. So let's download JCC into that. That should just be a quick small package if name resolution works. Yep, there we go. And there's already a folder inside of this zip file, so it's safe to just unzip it in our project folder here. Okay, we got all that. I'll clean up the zip file. We don't need that anymore. And you can see that we have JCC, which is the Linux executable. We have jcc.exe, which is the Windows executable. Unfortunately, the Linux executable for JCC is a 32-bit binary. And even if I install the 32-bit libraries, basically the multi-lib, the 32-bit compatibility packages for Linux, this Linux executable doesn't work for me. Specifically, the first problem I have, which ends up being the last problem because I can't get past it, is it seems to read characters doubled up from the source code input files a significant amount of the time, which of course just leads to endless syntax errors. JCC is not an open source program, so we only get the executables. We don't get the source code, so I can't try to build a 64-bit or a newer Linux executable that will work on a newer Linux installation. It's proprietary in that sense. It is freely available to us for non-commercial use, but if you go back and look at the license and look at the JCC webpage, there's a suggested donation, and then it's also for any kind of commercial use. If you're not distributing the source code of programs that you create with it, you would need to purchase a license to do that from Jason Winters. So unfortunately, this is not open source, but fortunate that we even have a tool like this available to us at no cost for non-commercial and hobbyist use. So I said the Linux version doesn't work, but the Windows version does work. And it works under Wine on Linux. So Wine is it's a program that implements the Win32 APIs natively on Linux. So you're able to run quite a bit of Windows programs, a significant amount of Windows programs on Linux. And it's not like software emulation, like an emulated virtual machine. It's actually native implementations of the Win32 APIs. So there isn't even particularly any performance penalty for running things under Wine if they work. So we'll be able to run JCC, the Windows version of JCC, jcc.exe, on Linux using Wine. So the first thing I need to do is install Wine. This is an Ubuntu system, so I can just sudo apt install Wine. And Wine itself is actually a 32-bit program. So you'll see I need to install about 379 packages here. This is basically another complete set of all of the Linux libraries and everything, but the 32-bit version of them, the i386 version of them. And then I suspect Wine is also pulling in a bunch of X-related stuff that I didn't have installed before because it can run graphical Windows programs. So that's all fine. I'm just going to let it install all of that. So it's going to need to unpack all these packages. This will probably take a minute since there were several hundred packages. So I will speed up the video here and talk to you in a second when this finishes. Okay, so Wine and all of its prerequisite packages appears to be installed. So we should be able to, and actually it's very important, I want to set the environment variable wine architecture to Win32. Otherwise, I think Wine tries to emulate a 64-bit Windows environment, which we don't need and doesn't tend to work as well for most purposes. So you can set this globally, export winearch30 equals Win32 in one of your shell startup scripts, but I'll just prefix the command with it so it applies to this command. And we should be able to run the jcc.exe executable here. Now, the first time I run Wine, it does a lot of setup, and it actually tries to pop up a little graphical dialog box with a progress bar or something while it's doing its initial setup. So you saw just a bunch of random error-looking messages go by. That's fine. The setup succeeded. You can see configuration in it created a directory for me, .wine, in my home directory has been updated. And then we see that it kind of mapped where I am to this Z drive, which is where it maps the Unix directory tree under this simulated Windows environment. It ran Jcc, and I'm getting the Jcc help text here. So if I don't provide any files to Jcc, we just get this output. So let's clear the screen and let's just run that one more time. And you can see that this time, because Wine had already done all of its initialization, we didn't get those hundreds of error messages about X windows not being available and whatever else it was telling us. We're just getting the Jcc output when we run it now. So that's great. So we have a Jcc Windows version of the compiler working under Wine on our Linux box. So that's step one. Let's go back up into that C directory. Now let me go back to my web browser. The other piece of the puzzle we need is this reader prep program. So it looks like this was originally written by Jim Morrison and distributed in the Hercules group, the Yahoo group, but it's no longer available there. So Jay Mosley is hosting a copy of that archive for us. So of course, Jay Mosley, a name that comes up quite frequently in my videos in this community. But his MVS FAQ has a section on how you can get data from outside of Hercules into your MVS 3.8 system. And one of the methods is through the virtual card reader. And you can prepare cards in an interesting way with this reader prep program. So we grabbed that. Let me download that back over in Linux. Let's paste that URL in. Not that URL. I get that in my clipboard again. Copy link. Okay, that URL. And this does not have a directory inside of it, so let's make a reader prep directory and unzip that file. So it has some examples of how its inclusion system works. It has a README. It has a makefile, but the makefile is a bit outdated and doesn't work cleanly on my system. But it's only a single C source file. So if you just compile that and I say I want my output executable object to be called reader prep, and I want to compile readerprep.c. Looks like we got some errors here, using some functions without including string.h. I remember running into this. Let me edit the C file. So it looks like there might be some control characters throwing things off here. So let's just delete those opening comments. And then I think from here on out, this program is good. Yeah, it's already including string.h and standard lib. So that error message was incorrect. I think there were just some control characters up top that GCC didn't like. So let's compile that again. Yep, perfect. So it compiles cleanly. It just had some characters that were confusing GCC. So now I have this reader prep program, and of course we just built this. So this is just a Linux program. I can run this directly. And if I run it, it gives me its help text. So what does reader prep do? Reader prep will read in a JCL file, and that JCL file can be in just an ASCII file, so we can edit it easily under Linux here. And it will turn it into an EBCDIC card stack. But importantly, it can also include other files. And it assumes those other files it's including are already EBCDIC or just raw binary, right? It's not going to perform any translation there. So the way this whole thing works, when we write our make file and do a make install, this is kind of the secret, right? So now we have our prerequisite pieces here. Here's what we're going to try to do. We're going to use Jcc under Linux, under wine under Linux. We'll use Jcc to compile our C input source file. And Jcc can directly output a symboled object code. So it can output S370 assembler, but it can also run the assembler step for us. So Jcc will give us our object modules. And Jcc also has a pre-linker utility that will link together all of our object modules, as well as any of the Jcc C standard library objects that are necessary to run our program. And it'll put all that together into one big object file that's then ready to link over on the MVS side of things. So we can write a JCL template that calls the IEWL, the system linker on MVS, and takes a data stream, an inline data stream in the JCL, which this reader prep program will include by including the output of Jcc and the Jcc Pre-Link utility, that object deck. And it'll turn it all into one big JCL job stream that we can then submit through the socket device card reader in Hercules. And we'll have a socket device card reader in Hercules that is configured to not translate from ASCII, right? It'll just treat the input as raw EBCDIC data. We will make a card reader in Jez2 defined to that card reader device, and it will just execute any jobs that we send into it. And that job will link our output from Jcc and some of these other steps and deposit the ready-to-run executable program in whatever PDS we want it to. So that's how this all works. And we'll string it all together here, and it'll probably make more sense when you see it, when you see all these pieces work together. Let's delete that. We don't need that anymore. So now it's all nice and clean. So let's make a directory for our actual Hello World project. So let's go there, and let's write our C code. It's hello.c. So we'll just do this quickly because this isn't a C tutorial, but it's exactly as you'd expect. We can do our int argc char argv, and we'll just printf hello again TSO and return 0. And my argv here should be it should be a double pointer, so pointer to an array. Okay, so does that look like it'll work? Standard C stuff. So I have my hello.c. So now just for kicks, right? If I wanted to compile that right now, I would set my wine architecture to Win32, and then I could use wine to run, it was one level higher in the Jcc directory, jcc.exe, and provide hello.c as the file I want to compile. Okay, so we need to provide Jcc the location of the standard system include path. And we do that by saying -I, and I'll just use my relative directories again. That's all under jcc/include. Okay, so that worked, and it gave us a hello.asm. So hello.asm. Perfect. So our Jcc works. It wrote S370 assembler for our C file. And we can go a step farther. We don't want assembler output. We want an actual assembled object model, object file. So the way we do that is we can say just -O. That will tell it we want an object module output. Okay, what did we get? Now we got hello.obj. And if we can just use something that can view, kind of do a hex dump. And XXD is cool because if you do -E, its little representation over on the side here, it will interpret the character set as EBCDIC. So you can see here we got an MVS S370 compatible little object module here with our compiled C program in EBCDIC. So that's pretty neat. Okay, so we know how to compile our code with Jcc and output an object module through whine, right? So this is the important command. We know we need to just kind of set up our environment for whine, and then we know we want to ask Jcc to give us an object output, and we know we need to tell Jcc where the system includes are. So we also have the Jcc Pre-Linker. So let's just run that manually before we try and put this all in a make file. This prelinker is prelink.exe. It also runs correctly under whine. And we can give it the, it takes the -S flag, and that tells it where we can pull the standard library objects from. So those are up in the Jcc directory under the objs folder. And we can give it the output file we want. So this is just going to be, let's call it hello.out. And then we tell it what object modules we want to include. So that's our hello.obj that we just created from the compiler. So let's see if that works. Okay, so there's a lot of output there, but you can see that along with our hello module, it's linked in all the modules it needs, all the objects it needs from the C standard library. So now we had our, our hello.object was nice and small, but hello.out has all of these other object modules kind of pre-linked into it so that when we call printf, printf is there. And when printf calls these string manipulation functions, they're all there. So that is our, we can look at it again with xsd hello.out. This is going to be our object deck that we need to link on MVS with the Mvs Linker. But it's all there. Also, how do we do that? So to do that, we're going to write our link JCL. And we'll give it a job card, right? This is just standard JCL at this point. I'll run it in class A. On my system, the held output queue is message class X. And we'll just have one step in this job. We just need to execute the linker. And again, all the individual modules will already be pre-linked into just this one input module for the linker. So that keeps it nice and simple over on the MVS side. So we're going to run IEWL, which is the MVS linker. And we can give it some parameters, map, list, xref. This will just control the output that it gives us. We're not going to build reentrant code. And I could put this on the job step, but let's give it 1024K. Let's give it a megabyte to work with. Like most MVS utilities, we need a sysprint allocation. syslmod is where the linker output will go. So I'm going to send my linker output into an existing data set. So disposition here is going to be shared. And the dataset name is going to be mwilson.load hello. So mwilson.load is a data set to hold load modules, to hold executables that I've already allocated. So if you don't have one already, you can allocate it and just copy the DCB of sys1.linklib. That'll get you the right attributes for that PDS. So basically, right, I'm saying this is the output where I want my program to go. And what else do we need? We need some temporary space for the linker to work with. So we'll just say any DASD and give it some cylinders to work with. That'll just be a temporary data set for the job. And then we need the input. So what is the input? The input is going to be an in-stream data stream. So this is a feature of JCL. And the delimiter is going to be $. And this is where we're going to use, this is not JCL syntax. This is the syntax for that reader prep program. We're going to include the ebcdic file, and we'll call it, what did we call it? hello.out. And then we put the delimiter to end that data stream. So now we're back in JCL syntax. And then we can just have a null card there to end this. Right? So if you've ever run the MVS linker, this should look familiar, right? We're just running the linker. We're telling it, here's where I want the output to go. And we are going to say the input to the linker is whatever gets included right here. Okay, so let's save that. So if I run that reader prep program now, let's just run that. And if I give the input to be my link JCL template, and I think I probably want to give it the output name. So let's call this maybe hello.jcl. So it's going to read the template link.jcl, and it's going to output the final card deck hello.jcl. Okay, so that hello.jcl is now in ebcdic format. So we're not even going to recognize the JCL that I had input. But if we look at it with XXD with the capital E option, hello.jcl, run through less so we can page it here. Here we go. So here's my now ebcdic card deck of JCL. So you can see the JCL that I put in, right? That's unchanged other than now being translated into ebcdic instead of ASCII. But if we go down to that input to the linker, you can see it's included all of those object modules. And so that's all of our compiled code and the C standard library object models. If I go all the way to the bottom of this, that's the end of the included data. Here's my JCL delimiter to say, here's the end of the end stream data. And then just that last null JCL card at the end of my JCL template. So we don't have a makefile to do that all for us, but that's what we're going to automate with the makefile. Now, the last thing we need to do is feed this job into MVS. Now, the way we set up our MVS system, we don't really have a way, sorry, not that job, this job. The way we set up our MVS system, we don't really have a way to do that yet. So if we look over at our, in Hercules here, let me hit escape. When we followed Jay Mosley's instructions for configuring Hercules and setting up the system, we got two card readers. We have the card reader on device C, and this is a socket device. So this is our card reader that's listening on port 3505. And we configured this one to interpret the input as ASCII text. So it's going to convert ASCII into EBCDIC. And this card reader is owned by Jez2. It's set up as a Jez2 input reader. Now, we can't use this because this expects ASCII, not EBCDIC. And I'd like to leave this around as an ASCII reader because we use that submit shell script to just send in, our JCL that we can easily edit in ASCII with our text editor. So I don't want to change this to EBCDIC because then we'll lose the capability to use that submit script for just simple jobs that we're sending in, and we're not doing this fancy. We want to get this, precompiled object deck in. We have the card reader at 1C, and this card reader is not monitored by Jez2. So I can submit whatever I want in Hercules to this card reader, but nothing will happen unless I then have a job on the mainframe that is reading from card reader 1C. So this is how we were doing things like for the job that installed the review front end and the review editor. We could make those kind of binary blobs available on this reader and then write jobs on the mainframe that would read from it. But that's not fully automated, right? We want to be able to submit a job externally that runs like this OC device, but it needs to be an EBCDIC. So what we're going to do is we're going to add a new card reader to our mainframe, and then we're going to update the Jez2 configuration to have a second card reader that it will accept input jobs from. So the way we do that is first we need to know, well, what would be a valid address for another card reader? And that comes down to the system generation we did. Part of the system generation is the I/O configuration for the operating system. And you can refer back to our videos, or you can go back to Jay Mosley's MVS System tutorial. But in this particular system, there is another card reader defined at address 1A. So we can drop in another 3505 reader device at address 1A, and our operating system nucleus is already configured and built to have an extra card reader at that address. If you're doing this on the TK4 system, you'll need to refer to the TK4 documentation to see how they set up their I/O devices, their I/O gen. But if you followed Jay Mosley's guide, you should be all set with a card reader at address 1A. So we'll update our Hercules configuration to add that card reader. And we then need to update our Jez2 to tell it, hey, Jez, go ahead and listen to, watch card reader at 1A and do something with it when jobs come in. So let's do the second part first. Let's flip over to TSO. And I'm going to log on here. And we can use RFE for this. So I'm going to go 3.4. This is in sys1.parmlib. So we want to get to sys1.parmlib. And if I page down, we'll see our Jez2 parameters 0, 0. If I was good, I would back this up. I'd have a way to bring Jez2 back up, even if I mess this file up and break it. But we are going to live by the seat of our pants and just do it live, because what fun is the internet if you don't see me break my mainframe again? So there are two changes we need to make in this Jez2 parameters file. The first is we need to tell it that we are increasing the number of readers from 1 to 2. So I think this will just have Jez2 allocate enough memory storage blocks to hold the control blocks for 2 card readers. And then if we keep scrolling down, we will see where reader 1 is defined. Yep, right here. So let's get that to the top. So reader 1, that's that existing reader at address 00C. Let's just copy that line. So I can copy, and I never remember, is it B for before? Yep, that works. So duplicate that line, change it to reader 2. Auth equals 0 doesn't mean authentication turned off. This is actually the types of activities this reader is authorized for. And I believe authorized, the set of 0 authorizations includes pretty much everything. So you can issue, jobs, console commands, all that kind of stuff. If you want actual security on this and authentication, you need to install a security product like RACF, either the IBM version or the differently spelled version that's available to us. And this is then just setting the defaults for the card reader. So input class A, I'm actually going to change this to message class X by default, since that's just where I like everything to go. But the important thing here is to change the unit to where our new card reader will be, which is going to be device 1A. Okay, so I've defined reader 2, it's unit 01A, and that will let Jez2 accept jobs as they appear on that new reader. So let's exit out of that and log off of TSO here. And that's really all the setup you need on the MVS side. And on the Hercules side, we need to add our new reader. So let's go back to Linux and let's edit our Hercules configuration file. If we go down, the card readers are the first ones defined here. So let's duplicate this line. So I just did YY and Vim to yank, and then I'll do P to put that yanked line. So we get a duplicate of the line. Let's change the address to, we said 1A. And the only other thing I'm going to do here is, we don't want this to do ASCII translation. This is going to be EBCDIC. I believe that's the default, or maybe not, but we'll be explicit here. We want that to be untranslated. Whatever we put into this reader will just go through to MVS without any translation. And we need to change the port number it's listening on, right? So this is the device type, 3505. This is the TCP port number that Hercules is going to listen on, because this is a socket device. So the way we send jobs into this card reader is by connecting to Hercules on port 3506 and submitting the data. So I just incremented it by 1 so we don't have a conflict with the existing port. So next time I start Hercules, that should take effect. But we can also just add that to Hercules dynamically. So let's go to Hercules and let's say attach. And I hope this pastes in. Yep, so we're going to attach, and then it's just that same configuration line. Okay, so if I hit escape now, it's probably off the bottom of the screen, so we're not going to see it up here until we next restart Hercules. But we now have card reader at address 01A, listening on port 3506, and this will be our EBCDIC input card reader. Now I'm going to switch to the MVS console. We do need to restart Jez2 for it to pick up those changes to the configuration we made. So we don't actually need to re-IPL all of MVS, but we do need to shut down most of it and stop Jez2, and then we'll start Jez2 again. So I'm going to start what looks like a normal shutdown procedure. We'll stop TSO. We'll stop VTAM. And we'll stop Jez2. I didn't stop the initiators first, so that might take a minute. Okay, that didn't take too long. So Jez2 is now stopped. But instead of doing a ZEOD and a QuiS and then re-IPLing from over in Hercules, I can just start Jez2 again. Okay, and now we get the startup options for Jez2. So reply 1, no rec. So it's just like I'm starting my system up again. All available functions complete. So now we can start, not ZNet, SNet. Okay, TSO started. So now if I go back over to TSO, I should be able to log on again. Yep, our system's back up and running. And let's see, what's the command? There's a command in Jez2 to show our input device status, just to kind of confirm that that reader is online. So this is going to bug me. I need to look this up. Is it Jez console commands, MVS? Enough. $DU, display units. Okay. So reader 1, which was the existing one, is inactive. Reader 2, 1A is showing as drained. So I think we need to start that reader. So we can $S, and then we can shorten that to reader 2. Reader 2 not available. Okay, let's see. What did we do wrong? Hercules, device O1A, bound to socket. So it exists in Hercules. Jez2 knows it exists now because it's showing reader 2. Is 1A a good address? Let's look back on Jay Mosley's site here. If we can get back to the root. If we look at his sysgen procedure, okay, here we go. So it is on the customizing your MVS installation. There's a reference of the hardware that we sysgened with. 2540R card reader, 0C, 1A. Yeah, so 01A is the correct device. The specific type isn't too important. So 01A should be good. So let's go back. We should be able to do this without re-IPLing the whole thing, but instead of further trying to debug and diagnose this, let's just try, let's just shut down entirely and re-IPL. Okay, and I'm actually going to exit Hercules. Let's just confirm our configuration here. Device 1A is going to be another socket device. Okay, that's fine. Start Hercules back up. Reconnect my console. Reconnect my TSO window. Then we'll IPL 150. Specify system parameters, none. R0, no rec. Hit F12 to go into roll mode. And what if we $DU now? Okay, it worked that time. So I'm not quite sure why, but apparently a full IPL instead of just stopping and starting Jez2 fixed whatever problem I had. So we'll start net. And now we are up and running. So let's go back out to Linux. And if we look at where we left off, let's go back into our, is it our C directory? Yep, and hello. So remember, we have that submit script we were using to send jobs in to our ASCII card reader with the netcat command. So we can do the same sort of thing. Excuse me. So if I do netcat W1 localhost, and now I'm on port 3506 for that EBCDIC card reader. And we can bring in our hello.jcl. That should have submitted a job, which it did, with the link step, and that link step completed successfully. So if I log on and I look at my data sets here, if I look at mwilson dot, what did I call it, load, there is our new hello executable. So let's run that. So one thing to know about the Jcc standard library that we're using with the Jcc compiler is that it's like printf and everything. It assumes that an allocation for the 3 standard Unix kind of POSIX, standard in, standard out, and standard error devices exist. So in TSO, we need to allocate a file called standard out. So printf has somewhere to print to. If we were printing to standard error, we would need to do the same for standard error. And then if we had something reading from standard in, we'd need to do the same. But for now, all we need is standard out. So we can allocate the file called standard out. And then the data set is just asterisk. That'll send it to the sysout output. So now if we call in our load PDS the program hello, we get hello again TSO. Okay, so that was what the makefile is doing, but we did it all manually. Let's go back over to Linux. We compiled with, let's see our command history here. So we compiled with Jcc and created an output object for our source code, our hello.c. And then we pre-linked our hello object with whatever other objects are required from the Jcc standard C library. And then we used that reader prep program to take our link JCL template, turn it into EBCDIC, and include that hello object. And then we submitted that whole card deck to our socket device in Hercules, our virtual card reader. And because we had reconfigured Jez2 to monitor that card reader for jobs, it ran that job as soon as it came in. And the result of running that job, the linker executable, is that we got our executable program output into wherever we told it. In this case, a partition data set called mwilson.load member name hello. So all that's left to do is to automate that. And we do that with a makefile. So really, really important to remember, set that environment variable for wine. So I'm just going to put that at the top of my makefile, and you can set environment variables in make this way. So export winearch space equals space, so not quite like in the shell. And this environment variable will then be set for any processes that make starts. And good makefile technique is to define some of these things as variables. So cc is traditionally the name of the variable that holds the C compiler you want to use. In this case, rcc is wine, because we need to run that Windows version of Jcc. It's wine, and then we'll give it the path to our Jcc executable. We need to use an include flag for Jcc, right? This is where we give it where the system include files are. We have our link command. This is going to be wine Jcc Pre-Link.exe. We'll just make a variable for where the linker objects are. So that's Jcc objects. May as well make a variable for where our reader prep program is. That's reader prep. And then we can also make variables for, well, where are we submitting this? I'm doing this all on my local system. So I can just submit to localhost, and then Herc port is 3506. But if you're doing this from a different system, so I've also set this up so that my desktop Linux system, I can do C development on and then submit to my Hercules instance running over on a VM on a different computer. If you, I think by default, Hercules just listens on localhost the way that we originally had it configured. But if you just put a port number in the Hercules configuration, sorry, let me look at Hercules here. Instead of restricting it to localhost, if you just put a port number, it'll listen on all interfaces. So my Hercules is configured to accept connections on port 3505 and 3506 from the world. Not a good idea if you have this box sitting on the internet, but I have a firewall that isn't going to let the outside internet submit to these ports. But again, make that a parameter, and then as things change, you can just update that here at the top of your makefile and adapt it to your situation. It's also nice to parameterize things like, okay, what is my target output? The output of this makefile is this hello.jcl. What do we want to call some of our intermediate stuff? So maybe my target library object file, let's call that hello.out. My source files, right now I only have one, hello.c, although we should take a quick look at the fact this works kind of no matter how big your C program is. Then our object files, and this is just funny make syntax, but objects, we're just going to translate all of our .c files into .object files, not obj. Right, so as we have more and more C input files, we're going to expect an object file for every C file. And then we'll just have a convenient automatically maintained list of objects to pass into that pre-linker command. So the first target that make encounters is the default target. So I always just like to have an all up top here, and this is going to build our hello.jcl. Our target rule, so hello.jcl, this depends on our objects being built, and it depends on that link JCL template. So assuming we have our objects, we just run the link command, so whine Jcc Pre-Link. We pass it the appropriate parameters, which is -s, and then where the libc objects live. And then the output name that we want, so that's going to be our target lib, since we made that a variable. And the reason it's nice to do these all as variables is because now I'm just going to reuse this makefile for other projects. And I just need to change what the stuff is called up here, and the rest of the makefile remains unaltered. So that's the output file. And then the input file to the pre-link program is the list of objects that we want to pre-link. And then after that's done, we update our final JCL output by running reader prep again, taking our link.jcl file, which is a template, and outputting that to our target name. Okay, so that's how we get the hello.jcl that we're going to submit to our mainframe. Is we assume we have all of our objects already compiled, we pre-link them, and then we update our hello.jcl by running reader prep to take our template and plug in the latest hello.out. Remember that hello.out name, that's a name that we used inside of our link.jcl template, right? We're telling it, include whatever's in the file hello.out here. So, right, if we use this for another project that's not called hello, we'd have to update our makefile a little bit. We'd probably want to update that template to use a name that makes sense for the project we're using. Okay, this says we assume we have all of our objects. Well, how do we get our objects? For this one, I'm just going to code this directly as hello.object is built from hello.c. And to do that, we run our C compiler with the -o flag. We include our include directive, and then our input file was hello.c. So with one file, that's not a big deal. As your project grows, you'll want to automate this within Make. You can write a little Make fragment template so that it knows how to turn a .c file into a .obj file by running this command. For our purposes, we'll just leave it like that. And then the last step is if we want to do that install target. Install depends on the hello.jcl being built. And we can just put that netcat command here. So nc-w1 connect to the Hercules host on the Hercules port and redirect standard in from our input file, from our hello.jcl. You can make a clean command if you want. That, rf, rm-f, all of our object files, our target lib, our target. Are there any other files that are going to end up littering our directory here? That should probably be good. So that's our make file. Let's make clean first and see what happens. Yep, that's the correct minimum set of files. So if we just make, it will compile, it will pre-link, and it will turn our link template into our hello.jcl. So it hasn't submitted to the mainframe yet, but we can make changes to our C code, printf, hello even more. We can run make again, and again, that'll compile, that'll pre-link, we get an updated hello.jcl. Then it's the make install step that will go one step further and submit that to Hercules through that socket card reader. So now if I go back to my TSO session and I say call load hello again, I get my updated code, hello even more. And of course, you can skip the intermediate, just make compile step, even more text. If you do make install, make figures out the dependencies and then it needs to rebuild the target. And so it will compile and submit. And now if I call load hello, we have our new version. So last but not least, what if I have a cool library function? Neat stuff.c and standard io.h, and we have another function here. This is going to be, maybe just void, make a function that calls hello, or that says hello from the function. And if now in my main hello program, let's just declare that void hello. Instead of all of this, if I just call my hello function, let's edit our make file. We now have two source files. We have hello and what did I call it? More stuff.c. Sorry, is that right? Neat stuff.c. Change neat stuff.c. Now again, right, I need to, in this version, I need to manually change this and make my neat stuff.c command. But beyond that, it'll automatically be picked up by the linker because it's in my objects list. And again, there's a way you can get more fancy with make and automate that a little bit more. But now if I make, it should, wait, were those errors? Overriding recipe for target. Sorry, did I mess something up here? Oh, I copied way more than I should have. Try that again. Okay. Let's pretend like I just created a file with a dot there. Okay, so if we make, it's going to compile all of that. Yep. Shouldn't see any errors. Perfect. Okay, so make install. Copy that up to the mainframe. Call load hello. And now hello from the function. So I have a multi-file C project that I can change easily under Linux, whatever editors, IDEs, anything I want in Linux. Hello again. I can edit my additional C file. Isn't this neat? If I type make install, my program ends up ready to run in my MVS 3.8 system. So I hope you think that is as neat as I do. I think that really makes it easier to write C programs for MVS. I guess if you're really used to the ISPF style editor, you really like the review editor, it's neat to work with when you're working in TSO on the system. But for me personally, I'm far more productive, especially writing something like C code, if I am using the editors I'm familiar with out in Linux and being able to manage my project that way. Right over on Linux here, I can keep I can keep this whole project in source control now. I can manage all of that from the Linux world, but then I'm able to target my MVS system with the build product of this C project using this neat technique. And now it's available to me over in my MVS world. So again, I was really pleased when I came across that source code that Tommy Sprinkles had been working on, and I immediately saw that as something where, yeah, I really want to adapt this technique and maybe actually try doing more C programming for MVS 3.8 because this really just makes it so simple. I can just focus on coding in an environment that I'm familiar with, and then easily flip back and forth between Linux, where I'm working on that code, and trying out my program in MVS. So I'll leave some pointers down in the description. I'll try and come up with a few things that I hope are helpful for you to get you up and running with this as well, so you don't just need to try and catch everything from the video and retype all of that. Let me know what you think of this technique. Are you going to try out C programming for MVS now that it's really easy to just work on your C code and deploy it, I guess is the right word, to your MVS mainframe? Let me know in the comments. Thumbs up, always appreciated, of course, if you like mainframe content and other interesting, non-Windows, non-x86 desktop system type content. Check out my other videos and subscribe if you want updates. Thanks a lot for watching, and I will see you next time.